across many circuits which are made up of number of resistors and cells interconnected in a complicated way. The formulae that we derived for series and parallel combinations of resistors and cells are not sufficient to determine all the currents and potential differences in such circuits. Hence, we use the Kirchoff's rules to analyze these complicated electric circuits. Let us study about those rules. Rule number 1. Kirchoff's first rule is also called Kirchoff's point rule, or Kirchoff's junction rule, or nodule rule. This rule is based on the principle of conservation of charge. At any node or junction in a circuit, the sum of currents flowing into that node is equal to the sum of currents flowing out of that node. This rule can also be expressed as the algebraic sum of currents in a network of conductors meeting at a point or node is 0. The current entering the junction is taken as positive, and the current leaving the junction is taken as negative. This statement can be expressed mathematically as sigma Ik, k ranging from 1 to n, is equal to 0. Let us now study about the second rule. Rule number 2. Kirchoff's second rule is also known as Kirchoff loop or mesh rule. The algebraic sum of changes in potential around any closed loop involving resistors and cells in the loop is 0. The electric potential at any point in a closed loop depends only on the location of the point in the loop. So, starting from any point in the loop, if we come back to the same point, the sum of potential changes must be 0. ABCDA is one of the closed loops in a complicated circuit. Starting from any point in the loop, we walk through the loop either in the clockwise or anti-clockwise direction and write down the change in potential. Let us start from point A and walk through the loop in the clockwise direction, that is ABCDA, and note down the change in potential. AB. While moving from point A to point B, we go from the negative terminal of the battery to the positive terminal of the battery. Therefore, the change in potential is plus V, which is the voltage of the battery. DC current I1 is passing through R1. The direction of current I1 and the direction of walk through is the same. The change in potential is minus I1 into R1. Here, you should clearly understand why the change in potential is minus. Charge always flows from a point at higher potential to a point at lower potential. Therefore, point B is at a higher potential compared to point C. We are calculating the potential change between points C and B, which is the potential at C minus the potential at B. Hence, the change in potential is negative. CD. Current I2 passes through R2. The direction of I2 is opposite to the direction of walkthrough. Current always flows from a higher potential to a lower potential. Therefore, the change in potential is minus of minus I2 into R2, which is equal to plus I2 into R2. Another way of expressing this concept is as follows. Here, charges are flowing from D to C. Therefore, point D is at a higher potential compared to point C. As we are calculating the potential change between points D and C, which is the potential at D minus potential at C, it is positive. dA, current I3 is passing through R3. The direction of I3 and the direction of walk-through is the same. The change in potential is minus I3 into R3. To apply Kirchhoff's rule 2, we add all these changes in potential and equate it to zero. Let us now apply Kirchhoff's rules to find the current in each branch of this complicated circuit. There are two important steps in the procedure. Step 1. We label and indicate the direction of current in each branch of the circuit. Next, apply Kirchhoff's first rule at every junction point. Step 2. We apply Kirchhoff's second rule to the closed loops in the circuit. The number of closed loops chosen depends on the number of unknown currents as per step number 1. Let us start with the branch AC for labeling the current and its direction. Current I1 leaves the positive terminal of a 10-volt battery. Therefore, the direction of current I1 is from C to A. Next, let us take the branch BED. Let us assume that the current I2 leaves the 5-volt battery from its positive terminal. Therefore, the direction of I2 is from E2 to B and D to E. The assumption that we have made for the direction of the current I2 may be wrong. In that case, at the end of the solution of the problem, we obtain a negative value for I2. Then we change the direction of I2 and write the answer. The three branches BA, CA, and DA meet at the nodule point A. We have already labeled the current in branch AC. We have to now label the currents in the remaining two branches. Let us assume that a current I3 is flowing in branch BA in the direction A to B. We are now left with only one branch, that is AD, to which we have to label the current. Let us assume that the current is flowing from A to D. We can now apply Kirchhoff's first rule to find the magnitude of this current. Next, let us take the nodule point B. Three branches AB, EB, CB meet at point B. The current in branches AB and EB are already labeled. We have to find the current in branch BC. Currents I3 and I2 are flowing towards point B. Therefore, the current in branch CB must flow out of the point. We now apply Kirchhoff's first rule to find the magnitude of this current. Next, let us take the nodule point C. There are three branches meeting at point C. Only the current in branch DC is not known. Let us assume that the current in this branch is flowing from C to D. We now apply Kirchhoff's first rule at node point C to find the magnitude of a current in branch DC. We have labeled the currents in all the branches. We have a self-check to see whether the magnitudes of the current in the branches that we calculated are correct. Let us apply Kirchhoff's first rule at node point D. As Kirchhoff's first rule is satisfied, the current in the branches that we have calculated is correct. There are three unknowns in the circuit. They are I1, I2, and I3. To find the values of these unknowns, We apply Kirchoff's second rule to any three closed loops in the circuit. Loop ABCA. Let us start from the negative terminal of the 10-volt battery. Walk through the loop in a clockwise direction and at the potential changes. Substituting the values of the potential changes across the resistors and that of the cell in the loop and simplifying, we get equation 1. Loop ADCA. Let us again start from the negative terminal of the 10-volt battery and walk through the loop in an anti-clockwise direction. Add the potential changes step by step and equate it to 0. Substituting the values of the potential changes across the resistors and that of the cell in the loop and simplifying, we get equation 2. Loop ABCDE. Let us start from the negative terminal of the 5-volt battery and walk through the loop in an anti-clockwise direction. Add the potential changes equated to 0. Substituting the values of the potential changes across the resistors and that of the cell in the loop and simplifying, we get equation 3. We have so far obtained three simultaneous equations with three unknowns. On solving these three simultaneous equations, we get the values of the unknown currents as shown. Substituting these values, we get the current in the various branches as shown.